I'd like to welcome today's speaker, Maximilian Kaipel, who's going to talk to us about the exceptional versus tau exceptional sequences. So thank you, Max, for agreeing to speak. I'll start whenever you're ready.
Yes, thank you very much for the introduction. And it's again a pleasure to see all of you, many familiar faces, a couple of new faces. And yeah, I will tell you about the project that I was working on very recently that I put on the archive earlier this year. And yeah, I'm quite excited to tell you about this. And I want to begin by basically writing down the main theorem, and then over time I will hopefully explain all of the terms and concepts that are involved. So yes, let's start. I'll write down the main theorem, and this concerns one particular class of algebras that I will fix or make clear now at the start. So I will consider this algebra that I call just AT, and this will be the Auslander algebra of the truncated polynomial ring. So this is just kx modulo x to the t for k some field. Let's just assume that we have it algebraically closed. I think it doesn't really make a difference, but some people have in the past assumed this. And so if I want to reference their results, I have to make sure that I'm using the same setting. So let's just assume that. I don't think it makes a difference. And let's fix some t, some positive integer. Then the result says that there exists a commutative diagram of the following form. On one side, we have here basic tilting AT modules. These are in bijection with complete exceptional sequences. So this is one of the words in the title. Let's say of AT modules. And the first, so I think this bijection was already known. The first new result is that these form a subset of, a subset of the set of complete tau exceptional sequences. Sequences of AT modules. Okay, just about squeeze that on there. So this inclusion, I think, is the first half of this new result, and so far it's not really a commutative diagram, but in some cases these objects admit a mutation procedure. So sometimes I can actually take a tilting module, remove one of its indecomposable direct summons, and replace it by a different one and still get a tilting module. So this operation, let's just call it mu I. This is some kind of mutation, and it's not always possible. But if it's possible, then we get the following commutative diagram. So again, we have here, of course, basic tilting, AT modules. Then there's a similar mutation process for these complete exceptional sequences. Let's call it psi r-1, giving us another complete exceptional sequence of AT modules. And similarly, there's a process of mutation of complete tau exceptional sequences. And actually, this is always possible. I guess I might just write a solid arrow for this. This is always possible. And what this thing is saying, this diagram, is that if these mutations are possible, then firstly, this diagram on the left commutes, so somehow the mutation of tilting modules is in correspondence with the exceptional sequences one, but this maybe you already know, not so interested. I'm more interested in the diagram on the right-hand side. So this is saying that exceptional sequences are also, or complete exceptional sequences are also complete tau exceptional sequences. And if I look at the mutation as a complete exceptional sequence, that is the same as if I do the mutation as a complete tau exceptional sequence. Sorry, a little bit of a tongue twister. So it doesn't matter which of the two mutation operations I consider, it will give me the same result, is what I mean by this. These are all some kind of mutation operations. Okay.
So Max,
This is the, yes.
just to understand, the phi map, it always exists.
Yes.
And so
this always exists.
That sometimes it restricts to a mutation map on this smaller class of.
Exactly. Yeah. So generally, the first main result is that there's an inclusion here. This is generally a proper inclusion, and I can mutate on this larger set of sequences always with this mutation phi that has a totally different definition to this mutation psi. But if I happen to be in this small subset, then I can use this mutation psi, and it will actually give me the same as this mutation phi. And the point is that the descriptions of these two mutations are quite different. So this is, it's not clear at all to begin with whether this mutation on the subset is a restriction of the mutation on the big set. Does that answer your question? Oh, yes. I hear Hipólito's voice from somewhere.
Yeah, yeah. So the question, so to go one step further from that, is that in general these mutations, I mean the mutations of basic tilting modules would not correspond to the mutation of the complete exception sequences. So it's not like a sequence of mutations, it's just one mutation always.
Yeah, right. So this is just about one mutation, just one step mutation.
Okay. Yeah. All right.
Yes. So yeah. So mu I replaces one tilting module, replaces one summand in the composable summand of the tilting module by another, if it's possible to get another tilting module. And this psi and phi operations are kind of operations on pairs, but they are very closely related. So I will also say later that basically this mu operation is possible if and only if this psi operation is somehow possible. And the problem you can run into on the left is that there may be just no other tilting module that has the same, that shares n-1 or all but one summand with the original one. And the process in the middle here, it's somehow always possible to mutate, but generally the mutation takes you outside of the module category. Generally, this is a process in the derived category. So what you will get when you mutate is not a sequence of modules, but somehow a sequence of objects in the derived category. And this is saying that if on the left-hand side I get a tilting module, then I will get again a proper module and not an object in the derived category. All right.
This reminds me a bit of this paper by Buan, Thomas, and Wright, I think. 3 kinds of mutation.
Mm-hmm.
Are you saying that this agree in a way?
I guess do they show something similar for hereditary algebras in this paper? I think maybe.
Yeah, but these mutations, they didn't always agree, right? I mean, it's like they studied it. I mean, the mu is like the mutation for cluster algebras, and then they have a.
Right. Yeah.
And things sort of didn't really go well always. Very nice.
Yeah, I'm not exactly sure, but I think the flavor is somehow similar. But yeah, this is yeah. I don't quite remember what they're doing in their paper, but I remember I looked at it and yeah.
So,
Right.
sorry, one last question. Does it
Yeah,
follow
go ahead.
just said that if you take the phi and you restrict it to complete exceptional sequences,
Yes.
now that it always produces again a complete exceptional sequence, then
Yes.
the phi will exist. You see what I mean? Because you said sometimes there are mu's and psi's, and when they
Right.
they are restrictions of the phi. And what I'm asking is, if the
Yeah.
phi restricts and co-restricts well, does that imply that psi exists?
Okay, I
And
guess
it's,
no. Okay, so maybe this is not quite. No, okay, so this is not true. Generally, this phi operation will take an exceptional sequence to a tau exceptional sequence. So
Right.
it might not yeah, it might not be an operation on this subset. Yeah. So maybe saying that it's a restriction is not quite
But my question is,
correct somehow.
it does.
Yeah.
Suppose that you don't know anything, you don't know whether psi exists or not, but you do know
Mhm.
phi exists. And it turns out that whenever you apply phi to a complete exceptional sequence, you get a complete exceptional sequence just by chance.
But this is sorry, but this is not true. It you have to apply it into like the right place. You need to know that it gives you an exceptional sequence.
That's what I'm saying. Suppose you know that.
Suppose I know that it gives me an exceptional sequence.
Yeah.
Yes.
Does that imply that psi and mu are well defined and that?
I guess so.
Okay.
But maybe I'm misunderstanding the question. But
The three maps are the three mutations are very.
That's okay. So my point again. Suppose that the set of complete exceptional sequences of eight T modules, seen as a subset of complete. Okay, you can apply phi to it, and you
yes.
get something. And it turns
Yes.
out that what you get is again the set of complete exceptional sequences.
Yes.
So then phi preserves that set. Does that imply that the psi and the mu are well defined? That you could that there will be a psi map?
I guess. I mean, yeah.
That's what
Yeah,
I mean.
I guess. I mean, if you restrict your attention to those phis for which the result is again exceptional, then you have constructed a map with that property that makes this commute, right?
Right. But maybe psi does not exist in that particular case. That's what I'm asking. Because you said the definitions are completely independent of psi and phi.
Yeah. So I'm sorry. I don't think I understand your question.
Okay, let's go on and maybe I can ask
Okay,
you.
maybe yeah. I can
Sure.
show you the definition of the I'll show you the definition of the mutation at the end, and maybe that can clarify something. Okay, yeah. Okay. So let's see. Let me explain some of the words that come up here and say some things about this algebra. So let's talk about this algebra AT. I said it was the Auslander algebra of this truncated polynomial ring, and what that means is that that AT is the endomorphism algebra of the sum of all of the indecomposable modules of this truncated polynomial ring. And there are exactly t of these, so there's one for every length between 1 and t, and let's just call these mi. And this has a quiver presentation as follows. We can write this as the path algebra of the following quiver, which just has t vertices and arrows going back and forth in a kind of linear way like this. Let's call these A1, B1, A2, B2, all the way up to AT-1 and BT-1. And the relations we impose is that anywhere in the middle, if we go to the right and then to the left, maybe I want this one. If we go to the right and then to the left, this is the same. Sorry, if we go right, this is the same as going around the left. So I'll just write this as AB minus BA. This holds at all the middle vertices. And then on the extreme vertices, I have a relation A1, B1 equal to 0, but not on the other side. So anywhere in the middle, going to the right, and then is the same as going to the left and back. And on the vertex number 1, if you go to the right and back, this is actually 0, so that's not allowed. But on the other end, at T, you are allowed to go to the left and back to T. So this looks quite a lot like the pre-projective algebra of type A. In fact, the pre-projective algebra of type A has this 0 relation also on the other side. And maybe some side notes that this is actually a quasi-hereditary algebra. And it has and the ordering of the vertices that gives you the quasi-hereditary ordering is exactly opposite to how I wrote it here. So 1 should be well, depending on your ordering. There's a unique quasi-hereditary ordering on this, and this algebra has global dimension 2 or 1 if T is 1, but okay. For most of them, it has global dimension 2. And now some kind of special classes of modules that we'll need to look at are as follows. So let's take a finite dimensional module, and we'll call it rigid if it has no higher, so that's what I mean by x greater than or equal to 1, so x1 and all higher x of M with itself is 0, and a particular type of rigid module will be called tilting if it is rigid, it has projective dimension at most 1. So in fact, we can ignore all the higher x's in this case, because we know that there'll be 0 from this projective dimension. And I will write it like, maybe I'll write it out. And the number of non-isomorphic indecomposable direct summands of M is equal to T. So this has N indecomposable direct summands up to isomorphism. And I will call, so this explains already, I guess, this word tilting here. Basic means that all of the summands are non-isomorphic. So that explains that part. Then some special classes of modules I'll need later are tau rigid ones. So these are modules that don't have non-zero Homs from or to their Auslander translation. This tau here is the Auslander translation. And finally, or maybe, no, penultimately, I will call it tau tilting, similar to rigid and tilting, if it is tau rigid, but now I have no more condition on the projective dimension. I just assume that, yeah, this number here is the same. Okay, that doesn't work. Yeah, I'll write it like this, M equal to T. So this is exactly this condition that I mean that I have up here. The number of non-isomorphic summands of M is again T. And one important thing to maybe keep in mind is that tilting implies, tau tilting because this condition of on the projective dimension tells you that, okay, maybe I write it out. Projective dimension less than or equal to 1 means that x1 m is 0 if and only if hom m tau m is 0. Okay. So every tilting object is a tau tilting object or module. And this general philosophy you can see throughout all of what is called tau tilting theory, as introduced by Adachi Yament, right? And you get a lot of classical concepts that behave very well for hereditary algebras. And then you put a tau in front of them, and then they behave almost as well for general finite dimensional algebras. So we can see this maybe with tilting and tau tilting. There is also this notion of a perpendicular category of a hereditary, or with a perpendicular subcategory in the module category of a hereditary algebra. And then Gustavo Hasso introduced tau perpendicular subcategories, and this behaves very similarly. And there's a lot of these notions. And if you now look at the theorem, you might think that, okay, this is actually then maybe not so surprising, exceptional. We just put a tau in front of it. Of course, it's going to be a subset, but you'll see in a minute that actually this is not the case for these two notions. So yeah, one has to always be a bit careful with these naming conventions and what they might suggest. The last type of object I want to explain is that of an exceptional module, also an important player in the first theorem. And this I will refer to an object as exceptional if it is rigid, and in addition, its endomorphism algebra is actually just the ground field. So that means that it has no endomorphisms that are not isomorphic. So no non-trivial, let's say, endomorphisms. And that will be all of the classes of modules that we will need. To illustrate this a bit better, let me perhaps give you an example of our algebra for a small t. So let's choose t equals 2. Then our algebra will be given by the following quiver and relations. So it'll be just two vertices, A and B, the arrows, and we will kill the ideal given by the path A and then B. So this is just this is the way that I compose these arrows here. We can write down its Auslander Reiten quiver. So these will be all the indecomposable modules as follows. And the Auslander Reiten translation will be illustrated here by these dotted lines. So you can see this is some kind of cylinder that wraps around itself. So you should kind of identify this two with the other two. Okay, so let's identify some of the modules that we have just talked about. Let's start with something quite easy. Let's look at tau rigid. So let me highlight in green here the indecomposable tau rigid modules. So any projective object has a trivial Auslander Reiten translation. So that means that our two projective objects here will immediately be tau rigid. And then we can see that the simple objects kind of form this orbit under the Auslander Reiten translation. So the tau of 1 is 2 and tau of 2 is 1. And of course, they don't have any maps to each other. So these will also be tau rigid. But we can see that here we have this module, which is the injective at 2. At 1. The injective at 1. Its Auslander Reiten translation is the projective at 1, but it does have a map factoring through 2 that goes there. So this is not a tau rigid module. On the other hand, let's look at exceptional modules. Let me highlight these in in red. Well, actually, now that I realize that Jose is in the audience, who is colorblind, let's maybe choose a different color. Let's go green as well. Blue, I mean. Exceptional module here, but hopefully the shape also differentiates it. So the exceptional modules will be as follows. These are maybe slightly more difficult to calculate, but definitely we can first look at the condition on the vanishing endomorphism algebra. This lets us get rid of one module that can never be exceptional, which is the projective up here, because it has a map from its top to its socle, right? So it has a map that goes like this and then back around. So it does not satisfy the second condition. It cannot be exceptional. On the other hand, again, every projective is rigid, and this one doesn't have any non-trivial endomorphisms. So this will be an exceptional module. And then the simplet 2 is also exceptional. The simplet 1 actually has a degree 2 self-extension, a non-trivial one. So it will not be exceptional. And this injective at 1 is also exceptional. So we can already see that not every indecomposable tau rigid is exceptional, and vice versa as well. Okay, and then maybe I write down the tilting modules. So the tilting modules are given as follows. We have 2, 1, 2 plus 1, 2 and 2, 1, 2 plus 2. These are our tilting modules. And then the tau tilting modules are 1 plus is just, so the non-tilting tau tilting ones is just this one on the right here, tau tilting. Okay. Are there any questions up to this point? If that is not the case, then let me continue with talking about the main players of this talk. These are tau and exceptional sequences, and then it will become quite clear that these are very different kinds of objects a priori.
I would like to make a comment.
Yes.
It's quite remarkable that in this already very small algebra, all the objects are different, right? I mean, you take any definition,
Yes.
take a different family of objects, and
Exactly.
quite illuminating in a way.
Yes, you can see that these two objects are really completely distinct by looking at these two modules here, really.
Yeah. And you have tau tilting, which is not tilting. I mean, it's split. These are very nice examples.
Yes, I think it's a nice example, and it's the smallest non-trivial example of this family of algebras that I'm considering here. And now, let's see what are these exceptional sequences. So this is a very classical definition. So I will be a bit lazy and not attribute it to anyone. It vaguely originated in like Rudakov's school of algebraic geometry, really. But we call a sequence, this was already in the 1980s or late 80s, early 90s. So a sequence ER to E1 is an exceptional sequence if, or let's say of AT modules. This is quite important because exceptional sequences are generally objects in the derived category. If each EI is an exceptional module. And secondly, if there's a certain orthogonality, semi-orthogonality, you could say, so we have no non-zero homomorphisms from EI to EJ whenever J is less than, sorry, wrong way around. Whenever I is less than j. There's always a bit tricky depending on how you order this. So the point is that you do not have maps going from right to left. So from E1, I cannot have homomorphisms to anything else on the left. I can, however, have morphisms from the left to the right. So ER could have a map to E1, but not the other way around. And similarly, the same holds for extensions. So higher extensions also only go in one direction, which is the same direction as here. So let's, yeah, and one more. Let's call it, let's say that it is called complete if this R, in our case, is equal to the number of symbols that we have. So in our case, it's T, but maybe in general, call this complete if R is the number of symbols that our algebra has. So in our example here, we have two exceptional sequences. Sorry. These will be given by the following. So 2 and 1, 2, and 2, 1, and 2. So we can see that definitely the things on the right don't have maps to the things on the left, but we can see that the things on the left generally do have maps going to the right, but that's not a problem. And also we have no extensions. So we have no extension with this one as, I always have to remember which way around this goes, but yeah, with this one as a quotient and this one as a submodule, right? We have one the other way again. So these are our exceptional modules. It's just, sorry, complete exceptional sequences. Complete exceptional sequences are these two. Okay, leaving some space to fill in some stuff later. Now, the power of these exceptional sequences is somehow most apparent when you have complete exceptional sequences. So there's some kind of consequences of if you have these actually complete exceptional sequences, and this tells you kind of their derived nature perhaps. They generate the bounded derived category of AT modules, and I mean this holds for all finite dimensional algebras, and they define also semi-orthogonal decompositions, which are just basically subcategories with the same orthogonality conditions as here, a sequence of subcategories, semi-orthogonal decompositions of, again, the derived category. And sometimes they can be used to construct non-trivial examples of Bridgeland stability conditions. So this is just to say that these are kind of nice and important examples of objects to have in our category. But, and this is the big problem, they might not exist. So stability conditions on this derived category. But now the motivating problem is that they might not exist. Complete exceptional sequences, and even objects, to be fair, exceptional objects, need not exist in general. Need not exist for arbitrary finite dimensional algebras. Okay, for example, let's take the algebra gamma, which is very closely related to our A2 example, A2 as in t equals 2 in our thing above, but now we're killing both paths of length 2. We can look at its Auslander Reiten quiver, which again looks very similar to the one that we had above, but now we have killed or we have kind of ruined the degree 2 self-extension of 2. So we used to have a projective here that kind of made sure that 2 had no higher x, but now x2 of 2 comma 2, sorry, so many 2's, is non-zero. So that means that there are only exceptional objects are these two projectives. So these are the only indecomposable exceptional objects. All exceptional objects are indecomposable anyway. But the problem is that these have morphisms to each other. So this one maps to this one, and this one maps to this one. So we cannot put them together in a sequence. So for this one, no complete exceptional sequences exist. And this motivated the definition of tau exceptional sequences. So let's have a look. A tau exceptional sequence, this definition is more recent, much more recent, and attributed to Buan and Marsh in 2021. They say that a sequence of modules, which let's call it MR to M1, is a tau exceptional sequence if this is a recursive definition. So if the first module on the right, M1, is now instead of exceptional, it is tau indecomposable and tau rigid, indecomposable, tau rigid. This is to replace our exceptionality. And now recursively, MR to M2 is a tau exceptional sequence in the following subcategory in what I call J of M1. This is the category of all modules X, such that there are no non-zero HOMs from M1 to X, and there are no non-zero HOMs from X to tau of M1. So in some sense, they're kind of tau rigid compatible. And the point of this is that this is actually equivalent to the category of modules of a different finite dimensional algebra, maybe not gamma because we had it up there, let's call it gamma prime, for some other finite dimensional algebra. And what makes this tricky is that in this, we have a different, or possibly different, Auslander Ryten translation. So just because something is tau rigid in this subcategory does not mean it will be again tau rigid in our starting category. Let us look at some example. So in this running example that we have here, we have, well, I've already spoiled that every exceptional sequence is a tau exceptional sequence. So these two are tau exceptional. However, we have two more that are 1, 2, and 1, and 1, 2, 1, 2. So we can see that in this exceptional sequence, we get a module that is not exceptional. In this tau exceptional sequence, we get that this module on the left here is not tau rigid in our original category, but in the reduction with respect to 2, we have that this becomes tau rigid, because if we look at the reduction of 2, we have to get rid of everything that 2 maps into. So that kills this entire line here. And then we have to look at stuff that doesn't map to tau of 2. So tau of 2 is 1. So we have to also remove 1. And basically all that is left is this module that injective at 1. And therefore it becomes projective and simple in this J subcategory. And that's why we can put it on the left, even though it is not tau rigid. Yeah. So yeah, I said at the start that this actually is one of the main results, that this is a subset of complete tau exceptional sequences. Okay. So you can already see that these definitions are quite different. And basically, the only thing that we know about the relationship before the theorem that I wrote at the start is the following. So Buan and Marsh showed in the same paper as they introduced this, that firstly, and this is basically the motivation for introducing them, is that complete tau exceptional sequences exist for all finite dimensional algebras. So this is to get rid of this problem here. They wanted to avoid this problem. And secondly, if my algebra, let's call it lambda, is hereditary, then in fact, the set or any exceptional sequence is a tau exceptional sequence and vice versa. So then the set of exceptional sequences of lambda modules is the same as the sequence of, and sorry, maybe I should have said complete again means that this index R here is equal to T. So yeah, complete if R is equal to T, or the number of symbols in general. They show that for hereditary algebras, these two classes of objects are exactly the same. And basically the point of why this is true is that, as we have seen here, X1 is the same as the tau rigidity for hereditary algebras. This is roughly why something like that holds. But this, of course, poses the question, what is the relationship between these two types of sequences beyond beyond the setting of hereditary algebras? And this was the starting point for my for my investigation, basically. So what is the relationship between these two types of sequences beyond hereditary algebras? And basically nothing else was known. There was one paper by Jacopo Nonis who showed that if I take a hereditary algebra and I tensor it by like a local commutative Noetherian ring, then my tau exceptional sequences will kind of be in bijection with the exceptional sequences of the original one. So you could maybe count that as a kind of vague relationship, but it's also still very closely related to hereditary algebras. And in general, we have already seen in this example here that if I take an exceptional sequence of length 1, it is not a tau exceptional sequence of length 1 necessarily, because we have this exceptional object. It forms an exceptional sequence by itself, but it's not a tau exceptional sequence of length 1 because it's not tau rigid, as we have discussed quite at length here. And in fact, you can also find the same to be true for complete sequences. So let me give you that example as well. It's also quite simple. We take gamma to be the path algebra of the linearly oriented A3 quiver, and we kill this ideal. So we just about make it not hereditary. This will still be a quasi-hereditary algebra though. And now the Auslander right quiver looks like this. And you can see that we have an exceptional sequence, a complete exceptional sequence given by this sequence of modules. This is a complete exceptional sequence, but it is not tau exceptional. Not tau exceptional. Why not? Well, we need that the objects on the left lie in this kind of J subcategory. So in particular, we need that hom of 2, 3 to tau of 1 to be 0, but this tau of 1 is 2, so this is not 0. So this cannot be, oops, this cannot be a tau exceptional sequence. Oops. Because this is not vanishing. So in general, we cannot expect such a relationship, as I have already told you at the start, for all classes of algebras. This does not necessarily hold. Okay, now let me give you an idea of why it holds for our algebra. And I will need one more definition in order to tell you. So this is a definition that goes back to Hipólito and Octavio Mendoza. So we will be interested in very particular ways of decomposing our modules. So from 2020, they say that if I take a tau tilting module, let's just take M to be tau tilting, then they call an ordered decomposition of M into indecomposables, which I'll write as M equals T, MT plus and so on to M1. Call this TF admissible, or at least I will call it that. Maybe they call it slightly differently. If now each MI is indecomposable, and we have this condition that MI is not generated as a quotient module by any of the modules to its right. So by any j less than I, mj. So this means that, that the module on the left is not a quotient module of any sum of the modules on the right. So this class of objects, this is the point. This is like saying that there would exist like some, what is happening? Some kind of power of these mj's and a quotient onto mi. Or maybe I even write this out to make it even clearer. M1 plus mj minus 1 to the r onto mi. This is what I want to avoid. Maybe this should be an I. Was there a comment or a question?
It's not. The
Yeah, I mean, so the gen, yeah, the gen means this, and then if you said not in there, then you want this to not be the case.
Yeah.
Right, this is, yeah, I hope this is clear. So now let's maybe look at this. Okay, good. So now let's take a closer look at the first line of the result that I wrote at the start. So the first main theorem is now saying that every complete exceptional sequence in the module category of our AT, our very specific class of algebras, is a complete tau exceptional sequence. Okay, and now I want to go into some details of how the proof work. So we are using one of the main results of the Mendoza-Treffinger paper, which says that actually these the significance of these decompositions up here lies in that they correspond bijectively to complete exceptional sequences. So their result says that there is a bijection between TF ordered decompositions of tau tilting modules. And I'll call this capital phi, and it maps to complete tau exceptional sequences. And this actually holds for all finite dimensional algebras, not just for our special class of algebras. And the way that this bijection works is that it sends my decomposition mt plus m1, sends this to, well, the sequence which on the right just has m1. And then on the left, I somehow take the largest quotient of m2 by m1 in some sense. So I will apply the torsion free functor fm1 to m2. So this is the torsion free functor of the torsion pair gen m1 perp. So it's the largest quotient of m2 which lies in m1 right homorthogonal. Okay, not super important. And then we continue this to the left, and here we have f, and then I take the sum of all. This is great. I can just zoom in. The sum of all the j less than I m. Sorry, maybe yeah. Sorry, j less than t mj of mt. Right. So every module we're taking the largest quotient that doesn't have maps coming from anything on the right. Okay. This is this bijection, which plays a very crucial ingredient. And now I don't want to look at all of the tau tilting modules. I want to restrict myself to tilting modules. So in here, I will have, as a proper subset, I have what I will call the quasi-hereditary ordered tilting modules. So by this, I mean that any tilting module has a decomposition determined uniquely by the quasi-hereditary ordering by just taking the idempotent at vertex t and multiplying it by t, and doing the same with all of the other vertices. I will call this t plus t1. And of course, one has to show that this is indeed a TF order, but this is true. And then let's look at what does this bijection now do? Well, it sends this actually, surprisingly, to the following. It sends this to the sequence T1, and then one realizes that this is actually a sequence of submodules. So T1 is a submodule of T2 and so on. And all that you send this to then is just T2 quotient by T1, which is well defined because they're submodules, and then TT modulo T minus 1. Okay, so this is much simpler and easier to understand than perhaps this expression up here. So you can just think of this as a sequence of submodules. This follows from some result of Iyama and Zhang, who study this particular algebra in terms of tau tilting theory. And we know now that this is by construction, because we have plugged it into this phi, right? We know that this is a tau exceptional sequence. So now what remains is to show that it is an exceptional sequence. Okay. In particular, there are two more results that we can make a note of. So there is Brüssler, Hille, Ringel, Röhrler from 1999, who studied exactly this class of algebras. And they show that the number of basic tilting modules, AT modules, is exactly t factorial. And then later, Hille and Plog in 2019 show that the number of complete exceptional sequences of AT modules is also t factorial. So in particular, because this is a bijection, I have t factorial tilting modules here. I'm putting in them into a bijection. I get, again, t factorial things here, which are all by construction tau exceptional. So if I can show that these are all now exceptional, I will have obtained that every exceptional module is of this form because of this counting. Okay, so it remains to show that these are exceptional, and I will not go into too much detail here. This is just some kind of diagram chase, basically. So it remains to show that this sequence T, quotient T minus 1, and so on, sorry, T1 is exceptional, which can be done from some diagram chase. Let's see how to write this. Diagram chase. And then you also use the following quite useful and very important fact that actually the endomorphism algebra of any tilting module is again isomorphic to your original algebra. This is also a result of Brösler, Hille, Ringel, and Wörle. And so you can show this, and then this proves the result. Okay, are there any questions about this?
Yeah, so this quasi-hereditary order that you have for your
Yes.
This would give you exactly the order for which this endomorphism algebra is also quasi-hereditary.
Well, the endomorphism algebra of any tilting module, well, the endomorphism algebra doesn't depend on the ordering, right?
Right, but the order gives
you mean
right.
Right. If you translate the ordering over, then yes.
Yes.
I mean, yeah, basically, exactly. So this TT will be, it's again isomorphic to the original algebra, and it will correspond again to that vertex T in the thing. So that would be the quasi-hereditary order, yes.
I see.
Exactly. So this very, very nice, this is a very nice, very useful fact for a lot of arguments that I'm using in this proof and in this paper. Yeah. Any other questions? If not, then I will take maybe 10 more minutes to talk about the mutation. Yeah, so just quickly again here, we had, in this example, we saw that you have inclusions here. I already gave this away. So now let's briefly talk about mutation. I will not go into too much detail. I will just say that there are kind of three different types of mutation that we're considering here. And to be really precise, I should really say that what I'm looking at is left mutation, even though right mutation is the inverse procedure. And so basically everything also works for, or everything works for right mutation as well, though perhaps the definitions will be slightly different. So generally, let's see, if we start with a tilting module T and I decompose it, I will make more precise what I said at the start. So I can take this T, I will apply mu I, and I get another tilting module, which differs from the original one only in the summand I. So I'll call this Ti prime, and then continues with the rest of the other summands. And the point is that this is not always possible. That's quite important to keep in mind. Similarly, we have for an exceptional sequence, let's look at ET to E1. I can mutate this and call that psi I. And now this is kind of a pairwise operation. So it will be an operation on the pair, kind of a local psi on the pair EI minus 1, and leave everything else unchanged. Importantly, these two things are not always possible. As I said at the start, such a tilting module might not exist, and this thing here might be an object in the derived category and not a proper module. However, for tau tilting, we can, for tau exceptional, we can always mutate tau exceptional sequence. So if I take MT to M1, this was introduced recently by Buan, Hansen, and Marsh in 2024. And this looks exactly the same as the exceptional thing at first glance. So it's just the same. Whoops. It's just also, again, a pairwise operation. M1. Okay. And now a small proposition that I mentioned at the start as well is that basically, loosely speaking, let's put this into quotation marks maybe, mi minus 1 is possible if and only if psi I is possible. So here, this should mean maybe here, this means there exists another tilting. And here this means psi ei minus 1 are modules, not objects in the derived category. This is quite important. Okay, now the final theorem. Yes?
The hypothesis here, so this proposition applies only for AT or is it general?
Yes, that is only for AT.
Okay.
For AT. Yes, that's very, very, very good to highlight that. Yes, very good to highlight that is only true for this AT here. And then, yeah, the second main theorem that kind of completes this diagram at the top says that, or at the start, sorry, says that if I take a complete exceptional sequence, let's call that E, and from this theorem, we know that it will lie in the image of phi of some tilting module, right? So let's just take note of this fact that E is phi of T for some T with a unique quasi-hereditary decomposition. Okay, this tilting. Then, so if this is a complete exceptional sequence in the module category, this is really important to reiterate, and it has the property that its psi I mutation is also an exceptional sequence in this module category. Then we can describe, or we can say that this psi I, of E is the same as the phi I of E, and it's the same as applying this bijection, Mendoza-Treffinger bijection, to the mutated tilting module at I minus 1. So in other words, it doesn't matter which of the mutation operations I apply, like whether I consider the mutation of exceptional sequences or the mutation of tau exceptional sequences, they will be the same and they will correspond exactly to the bijection of phi of this mutated tilting module that corresponds to it. So this, this is what I try to summarize by this commutative diagram, saying that if these mutations exist, then this diagram commutes. But maybe there can be a little bit of confusion about this. And now, just a quick word about the proof, because there's one, the proof is I will not go into any details. This is really the main challenge of these whole shenanigans. I think this showing that these two things are the same is not so easy. But fortunately, you can kind of reduce the problem. You can first show that this is true for I equals 2. So this means showing it for the rightmost pair, so for the pair that is, for E2 and E1. And then you can use this reduction, you can use a reduction result that I proved, which ties in very closely with what Hippolyto said about the quasi-hereditary ordering, which says that if I take this, if I take this kind of subcategory that I need to consider with respect to my T1, this is actually equivalent to the algebra with just one vertex removed. So exactly like Ippolito said, I look at the endomorphism algebra of any tilting module and I get again the original algebra. But if I now look at somehow the category that is orthogonal to the rightmost one, what will end up happening is I delete this vertex, which cuts off this, and the commutativity relation gives me that now AB equals two things that don't exist anymore, so they will be equal to 0. So, sorry. Actually, I think it removes it on this side. Sorry. Yeah, because M1 removes vertex 1, right? And then I need to have this 0 relation here. And at 2, I will now see, okay, if I go to the right, that's the same as going to the left, but on the left doesn't exist anymore. So this will be equal to 0. So that's how you can see that you have this reduction step. And then from this, you can basically follow that it's enough to show it for I equals 2. Yeah, that's basically everything I wanted to say. I brought one illustration from the paper for the T equals 3 case, so we can see the subset of complete exceptional sequences here. This has kind of the same shape as the mutation of tilting modules, because that's what this result here describes, that it corresponds to mutation of tilting. And then around it are some, but not all of the complete tau exceptional sequences. And we can see that if I take the exceptional sequence, I can apply phi or psi, and it doesn't matter. I will still get the same. I will still get the same complete exceptional sequence, but now I can no longer apply psi 3 again to this, because I would leave the module category and would enter boom, somewhere over here, the derived category, but I can still apply phi 3 and now get the proper tau exceptional sequence. And yeah, maybe this illustrates it a little bit more. Yeah, basically, this is everything I wanted to say. I can say more about the mutation, the definition of the mutation if you want me to, but yeah, that's everything. Thank you very much.
Thank you very much, Max. I found it very interesting. Do we have any questions?
Yeah, well, first of all, congratulations, Max. I mean, this is a very nice result and really nice paper.
Thank you.
I want to say also that Max has another paper on tau exceptional sequences with Buan over Terlan, in which they actually study the mutation of tau exceptional sequences depth, like how difficult and technical it is. I mean, Max has make a very nice story for us to follow and believe that everything works right, but I mean, there's a lot of work.
Thank you.
You know that, and yeah, so maybe I have asked in private this at some point, but and I will go again. Maybe now the question is better formulated, or maybe not. Okay. But you just said that you can apply phi, and when you apply phi, you go phi 3 in this case, and you go outside of the module category, right?
Mm.
So,
yes.
So I was wondering. I mean, I do not know to which side of the module category it goes, to the left or to the right, depending on that. If you can sort of approximate, the result that you get with the psi by the module category, and try to see you get back what you have with phi. You know what I mean?
Yeah. It's a very natural question. And I also wondered about this. I basically calculated a few of these mutations that leave the module category by hand, and I looked at it, and I couldn't really see I couldn't really see what the relationship would be. But maybe there is some relationship that I just didn't see. I have to say that I didn't try very hard to make it work. I just looked at it, I was like, looks like I don't know what it looks like, and then yeah, kind of gave up that direction. But maybe there's something more to be said there.
When you do,
It's definitely a very interesting, yeah, especially with the philosophy in mind that you
right.
want these tau exceptional sequences to replace exceptional sequences. Maybe this is somehow, maybe I don't know if this point came across. This is why I wanted to motivate this problem, right? Like the complete exceptional sequences don't always exist. So we want to create something that does always exist, but the problem is we don't know if it behaves in the same way at all as these objects that we wanted to replace, right? Like it, of course, would be too good to be true if we can get everything that we can do with exceptional sequences, with tau exceptional sequences, but now they always exist. Of course, that is maybe too ambitious.
Yeah.
But yeah, in the attempt to approach this replacement, one should try and really approximate the exceptional sequences also in the more general derived setting. But I didn't try to do this very hard just yet. But it's very interesting and it might work as well. But I couldn't see immediately what would be the connection.
In your calculations, you did it by taking complexes of modules or complexes of projectives, or how?
Yeah, that's a good question. Maybe complexes of projective is more natural. I'm not sure if I did that though. That would, if I was smart, I would have done that. But I think maybe I did it with modules, which is a stupid idea now that I think about it. Yeah,
Because
not sure.
I'm wondering if doing it with complexes of projectives or injectives, depending on which side you're approximating. I mean, you might have that your object is like a long chain of things, and then you do what you do with rotating theories, a projective presentation. So you take the first
Yeah.
and that might.
I would have to calculate again. I might try calculate again because yeah, I think it's also very interesting to answer if this is possible at all.
Yeah.
Yeah.
It's very nice.
Thank you. I'm also very happy with this behavior because this is what you expect, right? You hear exceptional sequence, or you basically hear any term, right? You hear any term, and then you put tau in front of it. It should be a generalization in some way, but for this, it's really not clear that it is. And so it was nice, I think, to show, if I may reiterate, that I like this result a lot. That actually every complete exceptional sequence is a complete tau exceptional sequence. Like this is how it should behave, if you ask me.
Yeah.
But yeah. Yeah.
So sorry, I missed, or maybe I misunderstood, but this is not true in general, right? Not every.
Exactly. Only for this AT algebra, it was I able to show it.
But are there examples where this is not true?
Yeah, so exactly. So for the complete case, so for the non-complete case for length one, I mean, this is kind of trivial. Length one sequences are just modules, right? So length exceptional sequence is an exceptional module, and a length one tau exceptional sequence is a tau rigid module, incomposable. And we can see that these are not the same in this example already. And for complete sequences, I had this example of this quotient of the A3 quiver, where you have this complete exceptional sequence, but it's not a tau exceptional sequence because this module is somehow not compatible with one, not compatible with the Auslander Weiden translation of one here.
Yeah, this brings back from us. This has a two cluster fitting subcategory, and this should be like a how-to exceptional sequence. I was trying to define at some point with Eduardo Marcos higher stratified systems, trying to relate them with higher
Yeah, maybe it could be something.
I tried
it. But this is it's also quasi-hereditary algebra. So a natural question is also how large can you make this class of algebras for which this works, right?
Yeah.
Like this is very predictive. But yeah, I mean, this example here is also quasi-hereditary, which is a property I use a little yeah, seems to not be strong enough. Whether it's true for all Auslander algebras, I don't know. I haven't really looked harder to find a counterexample, but there are many unique properties of this algebra that make this work, right? Like the endomorphism algebra having this property, this thing turning into a sequence of submodules, right? Like having exact counts of these types of objects, having this sort of result. So yeah.
Like the counterexample that you gave, I mean, this is a standard algebra, the algebra 2.
Right.
So it's 3 radical square is the standard.
Yeah. Oh. Is it really? Oh yeah.
Yeah.
Right, but anything in global dimension 2 is an Auslander algebra, right? Is everything that has global dimension 2 an Aus? No, it has to have dominant dimension also equal to 2, right? But yeah. Anyway.
Yeah.
So yeah, it's not known to what extent you can generalize this.
No.
But it's nice that it works for one class of algebras. Jose, did you have a question?
Yeah, if I may, all the questions led to something that I wanted to ask you about. Precisely there, I see. I think it's worth thinking about the quasi-hereditary structure. I can see right off the bat the difference between those two. You mentioned that the case that you proved, the AT, that it's quasi-hereditary and it has a unique ordering of the simples so that it is standardly stratified. But this one here, the example that does not satisfy your theorem or what you want, that is complete exceptional to be tau. This one has more than one. This one has 3 different orderings for which it is quasi-hereditary. And also, every time you have quasi-hereditary algebra, then you have a characteristic module. The characteristic module is always tilting, but in the generalized sense. So it doesn't have to have projective dimension smaller than or equal to 1.
Right.
But it is tilting in the generalized case. So I guess my question was, basically what you were discussing just now, in which ways you can use the structure of being quasi-hereditary and all of these properties to be able to extend your result. But I think it's worth thinking about it.
Yeah, that's a nice observation. I think I don't use the fact that it is quasi-hereditary as much as I use the fact that it has global dimension 2. The fact that it has global dimension 2 is very useful, exactly because you can then ignore, you have some long exact sequences, you can just ignore everything that has a 3, right? And higher. But it could be, so I don't think that the actual quasi-hereditary ordering is explicitly used, but it's quite possible that quite a few of these things are somehow shadows of that structure. Like these things having like particularly nice subsets in one direction, right? This could be a consequence of that. And yeah, it's not exactly clear to me where quasi-hereditary used or if global dimension 2 is somehow the more used property. Does that, yeah.
Yeah, that makes sense.
Does that make sense?
By the way, very, very interesting. Very good.
Thank you, Jose. I'm so glad that you could make it.
Do we have any more questions? Well, it doesn't seem to be the case, so let's thank Max again.
Thank you.